I'll probably have a question on the quiz around virtual memory. A possible question, the kinds of questions I might put on are anything from taking different algorithms, like paging type algorithms, and deciding which one might be better for a certain situation and why, to taking different types of page level designs or asking you to come up with your own for a particular situation. I may also ask you to do something like take this virtual memory for OO systems and talk about how the performance, what you think the performance characteristics of something like that might be on a Unix style paging, a virtual memory / paging memory management scheme. So just make sure you understand that stuff. If you have questions about that, you can ask me or you can ask the TAs. But were there any other issues there that people were unclear about last week that you want me to run through quickly before we start today? Okay, what is a distributed system? Well, again, there's lots of definitions. One of the definitions is it's one that looks to its users like an ordinary centralized system, but runs on multiple independent CPUs. Now, that's a very general definition, because something like that could actually cover, potentially a multiprocessor, like a 2 or 3 CPU machine. But more generally, the way I like to think of distributed systems are systems where you actually have these CPUs not all on one actual machine. So I like to look at the symptoms. And here's a set of symptoms that Schroeder came up with. One is that the processing units, there's lots of them. They're independent. That's good. Second is that processors communicate via a hardware interconnect. Typically, that's a network. The processing unit failures are independent. This is important. If you think about the processors this computation substructure out on the internet, one thing that you can't be sure of is that you're always going to be connected to a processor that's out there, and the second is that processor is always going to be up. Fourth thing is that there's a lot of resource sharing that has to be managed across this computational fabric. And the last is that there is state shared amongst all these processes. We had talked about some design issues before, more generally, when we were talking about systems. But once we start thinking about distributed systems, the design issues become more complicated and take on a different flavor. These are important to, I'll go through each of them and describe them, but keep these in mind because these are going to add more complexity. And when you read papers and when you think about systems, this is a good framework to think about, well, what's important and what's not, and what issues have they addressed and how have they addressed them. First one is scaling. So what type of scaling do we mean here? Well, because things are distributed, the idea is that you want to be able to add more processing elements to it. And that would be a great way to scale a distributed system, right? If you can just add twice as many and it just performed as well as it did when it had half as many. And so typically that's the type of scaling that you have to look at. Second is communication. Communication we almost took for granted before, but now, as I mentioned earlier, we can't take for granted. It's very possible that communication links can be severed. It's very possible that communication can be different within different parts of the computational substrate. And now your distributed systems have to have some way of managing that. And you'll see there's a paper called Grapevine that you'll see, which was a system done Xerox PARC. You have a paper on that, and communication is one of the biggest issues that they faced in developing this type of system. The third one is coordination. Coordination is if you want to do some kind of computation, how do you coordinate the different elements doing that computation? Could be a service too. So, for example, if you're doing an email service, how do you coordinate all these servers out on the internet? How do you coordinate updates to these different servers if you're doing something like DNS, which is a domain name service? Suppose there's one server at one place and you do an update there, and in another place on the internet you do another update and they're inconsistent. All right, there's a big coordination issue. This type of coordination becomes much more exasperated when you have the communication issues too. Transparency. In some distributed systems, as defined earlier, you want to make it feel like the distributed system is really one. This is a way to reduce the complexity of programming the system. And so transparency is just that. How can you make the fact that it's distributed transparent to the end user so that the end user can think about the system in a less complicated way and write programs more effectively? Naming is a huge issue. Naming is in essence indirection. So things like DNS is a big naming service on the internet, going from photo.net to some IP address 64.mumble, or being able to be able to figure out what services are out there and associating names with them so you can refer to them, so you can pass those references around. Load sharing. If you have all these independent computational processors around the internet or in your distributed system, how do you effectively utilize all of those resources? I mean, the reason you want to have all these, probably one of them is you want more speed, like SETI, right? SETI wants a lot of speed. How do you make sure that you put the right amount of computation on each processor? And you have to remember that if you don't do that, I mean, you can have, remember yesterday we talked about if you put too many processes on one particular server, what happens? Well, you can start thrashing, right? So you have to be aware of how to load share between your different processors. Consistency. So if you have computation state spread throughout the whole distributed system, how do you make sure that the data is consistent? So I mentioned earlier, what happens if you go to one server and you make one change, and you go to another one and you make an inconsistent change? Right, then you have an inconsistent system, and that can happen, and it will happen. And so your system has to have some way of being able to manage this inconsistency, so that the people who use the system actually don't get hosed by that, and they see a consistent system. Failures can happen, anytime, anywhere. They're not necessarily ones you can control. You can have lightning strike. You can have people go into tunnels and cut fibers by accident, and you don't know when how long. You can never predict how long a failure is going to last. A random failure is going to last. Security becomes even more important, as we've seen on the internet especially. We've had hackers come in and do a lot of denial of service type attacks. If you offer services on the network, someone could come in and try to hijack that service. Someone can try to hijack your servers. Because you don't have direct control over them, security becomes even more important. Heterogeneity really mixes all of this up. The big problem with having all these this distributed system like an internet, is that you have machines of different types, of different capacities, having different policies of use, and having different architectures. I mean, everything can be different, and so your distributed system, the way you design it, has to take that into account. And the last one, which is becoming more prevalent, is mobility. So think about something like WAP, right? You take your phone and it's web enabled, and you can go from one place to another. Or think about something like 802.11b, which is this wireless. You guys have seen these airports, Apple airports, with these wireless cards. You use it. Well, and imagine having a laptop where you take one of these around, not just in a building, but across the U.S. There's a lot now that a distributed system are becoming more and more mobile. You can't really assume that every computational resource exists in a specific location. So naming. What do we need to name? Well, there's a lot of different things that we need to name. There's processes, there's services, there's hosts, there's objects if you're doing anything as an object-oriented system, and there's groups of these things also. And when you think about naming, there's a process called binding. So binding is discovering and associating a name with one of these processes, services, hosts, objects, etc. You'll hear that term. You'll read it in some of the papers, and when someone talks about the binding states, they usually mean the two-part, this discovery and association. And an example of that is DNS. When you go out to the internet and you give an actual name to your server, to your clients, your Netscape or your Internet Explorer, it has to go out and figure out what the IP address on the internet of that server is. And so it has to discover that, and it has to resolve that into an IP address, and then it can bind it and then go and grab some data from that server. We're going to actually have a lecture on naming next week. It's important. There's lots of different reasons why you'd want to do that. And Nutella, when you guys did that client, you probably had some naming issues there, right? Like how did you do discovery of the servers out there?
Everything was IP.
What's that?
Everything is IP number. IP number.
So how do you get those IP numbers?
There are services that provide lists of active.
Right. And so how do those services provide that?
By using the Pong protocol, the ping and the Pong protocol.
So there's a protocol. There's a sense of you have to go out and get those IP addresses from somewhere, right? And so that's again discovery, and now your name happens to be the thing that you get back is this IP address. Communication. This is one of the most difficult aspects. So what makes communication difficult? Well, when you're communicating, the messages can have a lot of different characteristics. There's a length, some are short, some are long. There can be priority. And there can also be streamed or non-streamed. So let's think about the last two there. Priority. Well, why would you want to have one message have priority over another? And but why? Can you give like a concrete example, like a practical example of why someone would want to say, I want these packets to have priority over these other packets? 911.com. 911.com. So any type of emergency services over the internet. It's funny you mentioned that because the other day we were talking about the earthquake in Seattle. And it turns out that I have a friend who knows these guys at the U.S. Geological Survey out in California pretty well. And they have all these sensors all over the place. And they actually have up to like 30 seconds notice of when an earthquake's going to hit. And these alarms go off, and so they just get on. They're already in their safe place when these alarms go off. But wouldn't this be a great service on the internet, right? If you had your AIM client and you had this thing come and say like an earthquake's going to hit you in 5, 4, right? I mean, wouldn't you rather get that than like your next 3 junk email, spams or something like that? Well, that's a great example of a service that I would think would probably is one that you would see coming up. What's another good example of priority? Let's just think about the type of system, why you would want to integrate priority into a system.
Sending video signals or something that has to receive as a group, otherwise you can't view it.
Good. So if you're getting email versus video, you probably would rather the email, for example, wait for you to get your next video. Mm-hmm.
Or it could be exactly the other way around. You might want to get the video, but it's going to clog your system up, so you just want it to be low.
Good. You might, if you're in a low bandwidth connection, you might have that issue. So you might want to tweak the priority. One other thing that you guys that you may run into is increasingly these days in businesses they have gold level customers, silver level customers, and bronze level customers, right? And wouldn't it be cool that if you were a gold level, if you were the Amazon, buy where you bought a book every day, wouldn't it be cool if Amazon gave your packets priority over somebody else's, right? And there's ways that you can do that, both on the server side, but there's also with the new Internet 2 protocol, there's going to be ways that you can do that throughout the network. Streams. What are streams? What are streams? You've all heard of streams, video streams, right? What makes a set of streaming data different than a set of like email data or it's continuous, okay, it's sequential. What else? What's a typical thing what do you do once you get the stream?
Act on
You
the data
process
as
it,
it's coming in.
you act on it, if it's a video stream, you put something up, and then what do you do with that data typically? Discard it. You typically just throw it away. Now, why do you throw that away?
Because you've already done whatever it is that you want to do.
You've already seen it. Another thing is that a lot of times that data actually it takes up a lot of space. So if you're getting this video, do you really want to store gigabytes of video on your hard drive for all the video that you're watching or you're going to be watching? Probably not. So streams have a very different set of characteristics than your typical packets that you communications that you send. Now, the properties of the communication medium are going to affect the performance. So I don't know how many of these you guys have got into, but who can tell me the difference between bandwidth and latency? Have any of you heard those?
Sure.
Yeah.
Have those somebody who? Yeah.
Bandwidth is how much you can get through at once. Latency is more like how long it takes to start.
Okay, good. So the analogy I like to use is one of pipes. If you think of the internet as this pipe, bandwidth is what the radius of this pipe is, and latency is how long this pipe is from one end to the other. Okay, so if I'm doing video, what do I care about, bandwidth or latency? Bandwidth. If I'm getting streaming video, I care about bandwidth. If I'm trying to have a phone conversation over the internet, what do I care about? Latency. Okay, why do I care about latency if I'm having a phone conversation, Greg?
You want it to be sort of a real-time conversation.
Now I do care about bandwidth at some point, but these days voice compression is pretty good, so usually you can actually have a reasonable conversation over a 56.6 line.
Would you consider the phone conversation to be not streamed since they come in little packets? Separated, and you want them all. I mean, I guess everything comes in little packets.
Yeah, everything comes in packets, and I would think of it as a stream because it's stuff that there's no reason for you to want to store it or process it once you've heard it once. Process once, discard. Unless you are, government or something and want to keep this stuff around.
So with something like the video phone, then that's where you really want both. Right?
That's right. That's right. And video phones, they've been trying to commercialize those things for so long, and the problem is a lot of network. It's hard to have both good bandwidth and good latency.
Right.
That's.
But you could have, say, a real-time conversation, but delayed, like video images, right? In other words, could the conversation be real-time, but as he's saying it, you're not actually saying it?
And that's one of the optimizations, and you'll see that on video, typical type of video conferences. A lot of them these days have that. They'll sacrifice the video, but they won't the audio.
Right.
And they'll give it priority. They'll give the audio
Right.
packets priority over the video packets in that case. Multicast. Who's heard of multicast? Multicast.
One source, multiple destinations.
That's right. That's right. So why is multicast? How does that help us? What's so good about multicast?
If you can find a common path segment, you don't have to generate as much traffic as open at one path segment. You just have one message. You just split it at the end. Right?
Okay. Good. There was it was about, I don't know, 6 months ago, something like that. Do you guys remember this big horrible disaster that happened when Victoria's Secret had their first runway, their first show on the video, or they had something live, like some show live. What was their problem? What was their disaster?
Everybody logged in and it was super slow or very choppy.
Yeah, everyone logged in and it was super slow and choppy. So why would that be? Well, how would this work? So what happens? You have the VS server here, and then everybody starts coming in and asking for the same packets, right? And so this thing has to be sending out the same packets to a bunch of different people. What would be a better solution?
Send it out to one message to I guess, other main servers, and then have those main servers distribute locally.
All right. So multicast in this case. If you can have a multicast approach, then you send one stream out to different parts of the big routing centers of the internet, and then that gets rerouted. But you're only sending one stream until you finally get to the last layer where you actually have to split, and so that reduces your bandwidth or latency. Bandwidth requirements. Good. It also improves your server performance. And then message prioritization. How many of you guys have heard of this Internet 2, this new research project that's going on? A couple people?
Can't tell you anything about
Can't tell you anything about it. Well, one of the Internet 2 is supposed to be this new super high bandwidth, low latency network that's going to replace the Internet. There's a bunch of colleges now that are connected with new interconnects. I think they're all fiber, probably. But one of the things that people are talking about that this new Internet has as a part of it is message prioritization. Now, in the current protocols, there are ways to get message prioritization, but they're typically ignored or not followed. In this new Internet 2, message prioritization is supposed to be something that's obeyed all the way through. Part of the reason they're doing that is because they want to be able to do things like this video, data type, video audio type differentiation, any kind of multimedia. All those types of streaming applications are things that could really benefit from message prioritization. Unfortunately, I mean, like I said, it's in there now, but it's really, if you try to use it, it's probably not going to work too well. Now, here's a touchy issue: consistency. It's going to be one of the most difficult issues to deal with, and it's going to be, for example, in this Grapevine paper that you guys are reading. You really have to understand how you should try to understand how they manage consistency. Now, the problem here is that network links can fail at any time. It can be intentional, it can be unintentional, but they will fail at some time, and we don't know how long they'll fail. And so typically what people do is they say, oh, this is easy, what we'll have is replication. And what we'll do is we'll replicate the data strategically throughout our distributed system, and that way if it gets cut off, right, if something gets cut off, then the two pieces that are cut off can keep going on without having to worry about when this link comes back up. And people can replicate. You can replicate data. You can also replicate computation. If you send, if you're SETI, you can probably send, a couple. You can duplicate your computation in hopes that to make sure that one computer at least will come back with the answer if you think that actual processors are going to go down too. Now the problem with that is consistency. So what happens if these two, if there's a network failure and these two entities are sub-distributed systems are operating independently? Now, consistency is also an issue even if there is a connection because there's propagation delay, right? So if you're on one side of the internet, on one side of the coast, and someone else is on the other side, and you try to update some database with inconsistent data that's inconsistent, you might be able to do it, especially if there's a network link that's been cut. So how do you resolve that? Well, replication, actually, there's lots of research behind how to do that using replication. One of the ways that's typically used is some kind of voting scheme or what kind of majority scheme. So what happens is the person the system that has the most hosts that agree that this is the right answer is the one that wins. Another one is a time-based scheme, which is the most recent update is the one that wins. All of these different approaches have trade-offs. And you'll be exploring some of those in the Grapevine paper. But in essence, once you have replication, one of the things that one of the trade-offs is that you're going to have less effective resources. So if you're replicating data everywhere, then that's more disk space or more storage that you have to use that can't be used for something else. If you're replicating computation, which is more rare, you're getting less processing power overall. The trickiest thing here is how you manage extended failures. A lot of systems, assume that the failure isn't going to be for a long period of time, but you never know. Load sharing. Again, another active area of research. So what is load sharing? Has anyone heard that term before? If you're a SETI, for example, it'd be great if you could give more work to processors that can handle more work and less to those that can handle less. Same for any other type of distributed system. Now, the question is, how do you do that? Well, one of the things that helps you is that at least that processors that are more local to you, so say in your local subnet or so on, you can probably predict that those are going to have less communication failures than those farther away from you. That could be interesting. Sometimes it is, sometimes it isn't. But if you can't depend on something like that, then you have to do something like being able to migrate processes around your distributed system. So suppose that you're running, suppose that you're, as an example, suppose that you have some distributed system like this, and you say, I want to be able to run some simulation on these. Well, what you could do is start all the processes running on one, and then have that one start distribute the processes, start migrating these processes to other places on the network. And this works really well if you have a divide and conquer algorithm, right? Because you could say, suppose you could divide something into 3 pieces. You could say, oh, I'll take one, and then I'll give one here, and then one here. And this one might say, oh, I'll take one, and then one piece of the computation, I'll send one here and send one here. And you can have that sort of propagate out and have local process migration so that you can take an advantage of this locality that you know that you can predict that processors closer to you are you're less likely to have a communication failure than something that's many steps away from you. But this process migration can be expensive. And what's so expensive about process migration? It's not always expensive, but it can be. What's one of the reasons it might be expensive?
Well, you might have a lot of data that you have to replicate and ship.
Right. You have data and potentially program too. So if you have a lot of data, if you have a lot of program to ship, a lot of code to ship, then sending all this stuff over can be, I mean, if the cost of sending all that stuff over is greater than the cost of you doing it yourself, of running the computation yourself, then why send it over to begin with? So what, question?
Some parts of the problem have to be combined all at once, and yet one machine is much faster than the other. It's going to waste its cycles waiting for the next one.
That's right. That's right, and that's one of the problems you have with heterogeneity, right? You have some machines that can do the computation much faster. It'd be great if you knew which those machines were and be able to send them more so that you could give them more of the load than the other ones, so you get all the data back at the same time. You don't waste a lot of, and that's definitely one of the issues. Now, in addition to that issue, there's Turing completeness. You guys know what Turing completeness is, right? No? Oh, you guys haven't?
We've mentioned it many, many times,
Yeah.
but we haven't actually. We have that in May.
Okay, well, so here's one of the, if you have, each of these machines is what you can refer to as a Turing complete machine. So that means it can do any type of computation that any other machine can do. Now, if you have one of these, if you model any of these as a Turing machine, then you have what's called the halting problem. Have you guys heard of the halting problem? Mm-hmm. Okay, what's the halting problem?
You can't build a program that knows when it's going to stop or when it's something I'm not doing very well at articulating it, but
you got the general idea. You can't build a program that can tell you when another program is going to stop. Right. So suppose that the computation that you're sending out is one that has this property that you don't know when it's actually gonna stop. How do you know even if you know that this processor over here is 10 times faster than this one, how do you know that the piece of computation you send to one of them is actually gonna finish before the one that you send to another one? You don't. That's right. If it's a very regular thing. I mean, something like the SETI where you're just running a set of fixed computations, right? You don't need a Turing complete machine to do that. You can probably use some kind of modified state machine, and so you actually have a good idea of how long it's going to take. At least your predictions can be pretty good if you know what the resulting hardware is and what the load is. But if it's something like, compute the, imagine. Something that just goes off and compiles a program. You're doing a big distributed compilation, right? You don't know when it's necessarily going to stop, or what pieces of code are going to be harder to compile than other pieces. And so one other issue is propagation delay. And as an example, let me show you why that's an issue. Suppose that you actually had a computation that was well behaved, so that you could predict, how long it was going to run on one machine versus another. and that you did have some idea, and this is a lot of ifs, you did have some idea of how powerful these machines were. Well, the last piece of information you need to know to distribute the load well is how loaded the machines were right now at any point in time. If you have in a small network, that might not be so difficult. But if you have a large network that spans, the internet, what kinds of issues can you get to there trying to coordinate that?
So the machine says, I'm not busy, and then suddenly gets inundated from 100 friends with, here's your work.
Yep. So some machine way over here says, oh, I just came up, I'm a really fast, I'm a multi-processor, mumble, really, really fast machine. And what's going to happen? Well, everyone around it's going to start sending lots of work to it. But while they're doing that, this message is still propagating over to the other side of the network. And by the time the other side of the network, all of a sudden the whole network's sending everything to this machine. And now it sends a message saying, stop, 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 don't send me anything. And so everybody stops, and then all of a sudden it has nothing to do, right? So you can imagine getting into these weird oscillations where you're basically spending all your time batting off packets or waiting for packets. So if this kind of approach, which some people initially proposed, works much better when it's a local system where you have a lot of control. A friend of mine actually did a project at Xerox PARC around this. His name is Carl Waltzberger, and he had this great idea, which is that you treat all of these as the way that you assign the load is everybody has money, so to speak, and you do some kind of bidding for these resources. And he did actually a whole thesis on this, and is quite nice. If you guys are interested, I can point you to it. But the one really nice thing about reading something like that is it gives you a good sense of what all these issues are and how he went off and batted down a whole bunch of them. He's a great guy, really smart. And let's start off by talking about remote procedure call. How many of you guys have heard of remote procedure call? A couple. This was a notion that was introduced at Xerox PARC about 16 years ago. And what it does is so everyone knows what procedure call is, right? You call something else. Remote procedure call, RPC, just abstract the notion of where a computation runs. So the idea there is when you call something, normally you know that or you have some idea that it's going to run locally. Under RPC, it actually may run anywhere on the network, and you'll get your answer back to foo, just as if you had run a normal procedure call. So let's think about that. Now that we're doing remote procedure call, the standard semantics of procedure call, there's a lot of assumptions built in that we can't have built in anymore. What's the key one that we can't assume anymore? What do you always expect to happen when you call some procedure? That it comes back, right? Can we just assume that anymore? Can't assume that anymore. So the computation can fail. And there's different ways that it can fail. And some of them may be predictable in advance, some of them may not. But now, when you call a procedure, you have to be able to have some way of specifying what happens if this procedure doesn't return. So what's one way? Can anyone give me an example that we could change a procedure call by adding some other? Let's say we add another argument that helps us control this. What kind of argument would that be, and what would the semantics be of the resulting procedure call? Let's take a guess. Okay, timeout. Okay, and so how would that work?
Well, you specify how long you're willing to wait for a response, and after that it decides, oh, okay, fine, it's dead.
Good. So one thing you could do is to say, well, let's make, I'm just using scheme syntax here, let's make the first argument here be a timeout value. Seconds or whatever you want. But the point here is that the semantics are now, if you wait for more than this amount of time, then you generate an exception or do something depending on the programming language that allows you to know that this procedure call failed. Now at that point, what are your choices? What can you do if that procedure call fails? You can retry. You can call it again. What else can you do? Give up. You can give up. You can try to run it locally if the reason you were sending it off was because someone else you had it was a tough computation to do. Well, you're not going to get it from anywhere else. You might as well do it yourself. There's a couple options. You can do whatever you want, but those are the two typical types of things you might want to do. There's this notion of blocking versus non-blocking. And what is that? Has anyone heard of this before?
It's whether we stop and sit around and wait for the response to come back or carry on with the business.
That's right. So one other thing you can do is you can say, well, when I run this command, when I run this procedure called foo, am I just going to stop and wait and everything just kind of halts until the answer comes back or not, depending on the timeout? Or am I just going to immediately go ahead and then later on when the answer comes up, it'll just, then I can deal with it then. Now one way to implement this is imagine that the result of this foo isn't needed until later on in the computation. You could say, well, this is non-blocking, and then what happens is the computation will just continue until the point that it actually needs the result of this, and then it could decide what to do at that point. Right? So that way you can actually run two things in parallel. And I mean, there's some, even in Scheme, there's actually versions of Scheme that do something like this. Some of the semantics you could have, you might not decide you don't want timeouts, and what you have are non-blocking calls, and then when you make these procedure calls, it just runs, and it just waits, and then when it gets the result, it keeps going, and then it waits for the next one, and so on. That's one way to get concurrency without having to deal with a lot of the issues around concurrency. There are still some trade-offs to be made there. Now, just very quickly, do you guys think there would be any cases where you would be non-blocking but it wouldn't matter if the answer never came back?
There's a later if statement that would use the result in the condition that the if wasn't met. So
yeah, that's a good one. That's a good one. So if there was suppose you're getting some input from a user, right, and the user hit connect or click to do something, and then so you're going off to do something, and then later on the user hit cancel, right? You would never need it. There's a lot of different, but there's others that you might be able to think of, but there is both of these blocking versus non-blocking. That's an important distinction that you have to make, and when you're looking at an RPC, you have to understand whether the RPC you're using supports that. Another one is synchronous versus asynchronous. Now we talked about yesterday about synchronous and asynchronous. What's an asynchronous type of event? Keyboard input, getting packets, right? What's the opposite of that? See? Something that's clocked or something that you're definitely going to get back, right? So for RPC, you can have event-driven types of RPCs also. So this gets back to the notion of, imagine that you're calling something that you say foo, this thing goes off and has to wait for some asynchronous event, right? That might be something where you're not sure if it's ever going to come back or not, and as opposed to something where you need to know the answer in order to continue the computation. This here overlaps a little bit with this notion here, but I just bring this up because there are some pieces out there in the literature where you have this is what they call their distinction. This here, asynchronous versus asynchronous, has usually used more in real-time type systems. This last piece here is actually quite important. So this is the notion of, let me see, at least once, at most once, and exactly once. The question here is, when you do an RPC on foo, what happens? What can you guarantee happens on the other side? At least once semantics means that what the system will do, the distributed system will say, okay, I'm going to run this, I'm going to run foo, and I'm going to guarantee that at least one invocation of foo is going to occur. So you might want to do that, for example, if you have a very unreliable network, you might send it off to 2 different computers, or you might send it off to one and there's a timeout, and then you come back and you send it off to another. And that means that you might have actually more than one actual completion of this computation. So when would you want to have at least once semantics?
When you've got a complicated computation that has to be done, but all you care about is the answer, and you're just going to take the answer that comes back and use it.
Right. So if you're doing something where you're like a mathematical simulation or something where there's just a straightforward type of computation, definitely is at least once is perfectly fine. When wouldn't you want to do at least once?
When it alters the original data.
Yeah, when it alters data. So when you have side effects. So think about your ATM machine, right? If you hit the ATM withdraw button, and it says and it does an RPC out to register that with your bank, you probably don't want at least once semantics on that, because you could have lots of withdrawals registered, even though you get money once out of the machine. What about at most once semantics? Now that we know what at least once is, what do you think at most once is?
Well, I don't see the use for it, but I'm going to send out a single request. That's it. So with side effects, we would send out at most once. But this is at most one attempt, or at most?
Most once execution.
So we actually have to avoid a timeout. If there's a timeout, we'll send out another RPC
well,
because we didn't succeed.
Well, you have to be a little bit careful, because when you have a timeout, unless you know why the timeout happened, if you send out another one, you might get at least one semantics.
And therefore run it.
Yeah, because imagine you send off a call, and then the network, someone cuts the line, some guy in some manhole cuts a line. And so this line, your network connection may be severed to that part of the network for hours. And so then you send something off somewhere else. In the meantime, both of these might have succeeded, right? If you know that the timeout happened because of the actual computer on the other side, it was down, then that's okay. But it's usually you would get something back instead of having the timeout exception, if that was the case.
So the distinction between at most once and exactly once is a business letter comes to you and it says return, if not a deliverable to the addressee.
Yeah.
You'll take over.
Yeah. I mean, there's all sorts of things you can do with acknowledgments to try to know whether the machine on the other side got it. There's always some room for failure, but in general, you can make some assumptions that are pretty safe about timeout and getting acknowledgments back. But the key here is the difference between these two is that in this case, if you have at least one semantics, then they can be one or more invocations of that procedure. If you have at most once, then you had either 0 invocations or 1, but you don't have any more. And then the third one is exactly once, which is that this thing's going to happen, and it's going to happen at some point, but it's not going to happen 0 times. It's not going to happen more than once times. It's going to happen exactly once.
What's an example of something that we don't care if it runs 0 times or 1 time, but we do care if it runs more than 1 time?
Anything that modifies state type data.
Why would it be all right for it to run 0 times? I can understand exactly once, but 0 times doesn't seem to make sense.
Well, 0 times, one of the cases is that after you try to run it, if the result of running it doesn't matter. So suppose one of the things you wanted to do was to send out, think about streaming, right? Remember, with streaming, if you don't get some packet, then at the right time, then what use is it at that point? So think about the things that you would want to use for at most once. Think about things that aren't going to matter after some amount of time. And but that if you do it twice, I mean, you might imagine you get all this jitter, and because you're sending you're processing, all this voice data or this video data, right? You don't want to be sending lots of frames if you're using some kind of distributed system to do all the video processing for you. So that's a kind of thing. Anytime where you just the time value of the data is a good example of that. And exactly once is probably more like your ATM. Right, where if the ATM gives you the money, you want exactly once type of semantics if you're doing RPC between the ATM and the server that's managing that particular bank's ATMs or the system.
It's allowed to fail then at most once. could work, right? I mean, it would be okay if it told you we couldn't do that transaction, but no money gets deducted, right? I mean, it's on the ATM, if it says, sorry, couldn't do it, try again later, as long as no money is deducted, that's not such a terrible thing.
Yeah, though.
The only terrible thing happens when it deducts more than one.
Well, the interesting thing about that is customers get very upset when they go to the ATM and they don't get any money. So typically the way there's actually some interesting papers around these, how these ATMs work. What they'll do is if you're authenticated, because they take a picture of you and everything, if for some reason the link goes down, which it can, they'll actually give you the money and then try to do it, and then try to run the transaction later. Because they assume that most of the time it won't be a crook there taking this money, and that way the customer doesn't get upset. And so, in terms of retaining, like the customer service costs and retaining the customer, I guess it ends up working out for them. So this is, if you want to rob an ATM machine, right? Cut the link and.
Is there a way to do an exactly once where you actually send out the RPC to multiple servers, but then somehow there's communication so that as soon as one of them succeeds, the rest of them give up, or does it necessarily mean that you only send it out to one person at a time with
that most ones?
Yeah.
You typically, in all of these, you typically just send it out once, and that's because you don't. If everyone was sending out multiple requests, I mean once at a time, what you'll do is you'll send it out once, and then if you get a timeout, then that's when you have to decide what you do. So if you get, for example, in at least once, if you get a timeout, it's always okay to send out another request. What you don't want to do is just keep sending out a whole bunch and then wait for something, because if everybody does that, then then you've effectively reduced your overall processing power very quickly. So one of the assumptions that RPC makes is a client-server type of framework. And the RPC infrastructure has to implement a bunch of different pieces of it. So let's see what that actually looks like. So at one side here you have a server. On one side you have a client. And then you typically have some kind of discovery server somewhere out here. So what happens first? Well, the first thing that happens is the client needs to figure out if it wants to do this RPC, where these servers are out there that it could send this to. So there's some communication that goes back and forth here, and the client will say, I'm looking for a service that computes, extraterrestrial, SETI type things, or I'm looking for a Kerberos type server for authentication, whatever that might be. Now, once the client has that, it knows how to address this server. So it makes a call. And at that point, when it makes the call, this is all on the client side. Let's put the network here. When it makes the call, it does what's called marshaling. To the arguments of the call. And marshaling means taking these arguments and turning them or packaging them into something that can be sent over the network and recognized by the server. So once we get, then we can go through the network, find our way over to the server, where you do unmarshaling. The server then gets this request, processes it, and then you have on the return trip the same type of thing. You have your marshaling through the network, unmarshaling, and then a return. Now, why do we need marshaling? Well, different computers store their data different ways at all different levels. So for example, if you have a 32-bit number, do you order the bytes where the most significant byte first or the most significant byte last? issues like that. If you have integers, on some computers integers can be 64 bits, on some they can be 32 bits. And there's all sorts of reasons that data might not be the same here, represented here, as it is over here. And so you have this marshalling step that helps you out.
Is that some kind of sort of common syntax that everyone has agreed upon to use? Or?
That's right. That's right. It is. Everyone who's in the system has to agree to the same type, the same schema, or the same way of marshalling and unmarshalling, and you have to decide what types of arguments can be marshaled and how they're represented. All of that has to be very well defined. And you'll see, if you look at Microsoft.NET, which is the most, the newest, snazziest version of RPC, you'll see that they do a lot of work in this marshalling, because they do things like in Microsoft.NET, you can have lots of different languages. You can have these servers, the services written in a variety of different languages, Scheme, C#. The idea is anything, Java, anything goes. I don't know if Java, because it's Microsoft. But and the client here has to be able to marshal things, and they have to be unmarshaled back and forth, regardless of what language is being used over here.
What's the role of the discovery server again?
The role of the discovery server is for you, the service here, is for you to figure out what server out there provides the service you're looking for. So if you say, I want a Kerberos server, well, if you know what it is today, tomorrow it might not be up. It might be, or there might be some, maybe that one had a bug and they shut it down and someone else brought a different one up. Maybe there's one closer to you. Yes?
So that server has to already be registered somehow in the discovery server.
Yep. So that actually, when a server, and actually we're going to get to that piece of it also, is the whole registration. But this is just here. This is the generic how RPC works through the network. Now, there's a couple other pieces of this. You really want some kind of support to be able to do all this work for you. So typically this is done by the compiler or the linker. And what happens is that this step here, all of this actually, all this work is done by a component called the stub, which is generated by your compiler or your linker. And the stub, what it does is when a client does a procedure call, there'll be if this is a registered remote, something that can be done remotely, the compiler or linker can generate some code that makes it look to the client, to the process or thread that's running, as if this is just a regular call. And depending on, it might integrate a variety of the semantics we talked about before, but that depends on how you design this. But what it does is it implements all of this. It implements the discovery aspect of it. It implements the marshalling. It implements the unmarshalling. And so that way, when you're writing these things, it just makes it a bit easier to use. It also makes sure that some of them handle some concurrency issues that you might have when you're calling back, when you're doing the RPCs. Now, RPCs is used by NFS and AFS, which is the Andrew file system, but X doesn't use it. So there's lots of different ways that you can do distributed computation. This is one that's common, but there are many others that people have tried. So getting back to this part down here, anytime a server comes up, or if it goes down gracefully, it has to interact with some kind of discovery service. And typically there's discovery servers which around the internet or around the network that you're dealing with. And what they do is each server has some list of services that it provides. And typically these services consist of two parts. One is the name of that service and the version. And the name, these are typically integers. And what it does, the server will take this and go out and hand it off to the nearest discovery server. And then that discovery server can propagate that to other discovery servers. Now, one question is, if you think about that a little bit, you'll notice that, well, how does the server discover the discovery service to begin with, right? And at some level, what ends up having to happen is that something has to be hard-coded in, or there has to be some protocol for doing that. Like, for example, you send out some message out saying, I'm looking for a discovery service in some, just as a broadly, like a multicast message or something like that. There's an example of this type of thing is when you're, how many of you guys, have you guys done any sort of home networking? Do you guys have any home networks, or who has networking experience here? Anybody? Has anybody done? Okay, who does? Okay. So one of the things that you can, when you're doing networking, let's say you have a little network set up, you need to figure out what's my IP address, right? And you can have IP addresses that are static that you just build in, or you can have dynamic IP addresses. And so if you have dynamic IP addresses, it means anytime you need an IP address, you wake up and you say, okay, there's some server out there that'll give me an IP address that's handing these out, and I need for it to give me one, right? But the question is, how can you know what that server is, and how can you contact it if you don't even have an IP address? So that's an example of where there's a protocol, there's a way where you send something out, and in a way that you can communicate back, and that is very something specific that IP address server will see and say, oh, okay, here's your IP address. You guys are running Linux, okay. Okay, now one issue here, once these servers are registered with the discovery service, there's some issues here. When you're a client and you go to a discovery server and ask for what server provides a particular service, one of the questions is, well, which of the servers that are out there do you want to return as the one that you should use? And so the issue there is, again, load balancing. You want to be able to balance the load out, and so these discovery servers can actually help to balance the load amongst different machines by deciding which server to return back that you can use to respond to a particular service that you want to use. So let's talk a little bit about marshaling. Marshaling is important because it's the way that we get data back and forth. And as we spoke about before, you have to assume that there's a heterogeneous environment, which means that these servers on the other side are going to be representing data in quite a different number of ways. They could have, even at the very lowest level, at the processor level, they could be representing data very differently than the client does. The thing that you can get out of making the data actually match closely from here to here is that the less work you have to do in marshaling, and in marshaling, the faster your RPC will be. So typically what you get when you see one of these specs, one of these marshaling specs, is you'll see something like a common representation, which will say, here's a set of data types. So you can have integers, maybe different types of integers. You can have floating point numbers. You can have arrays, say, of data. You can have structs, maybe some more complicated aggregates. Bunch of different types. And then on the other side of this, you'll have a representation. And one type of representation is to just say, well, if we have, say, 16 different data types, you could have a tag that tells you, for each of these, that tells you 0, 1, 2, all the way down, that tells you what the data type is. And then on the other side of this, you'll have something that's a representation. And it'll say, for example, for a floating point number, here's how you represent it. You have to represent it in 64 bits. The first few bits are this part. The second few bits are this part. This is the exponent, and so on. And so this is what, when you read these things, when you read these specifications, this will be the meat of that. Now, one question is, what do we do about pointers? So pointer, points to somewhere in your process's address space. You can have a pointer in the client here that points to some place in memory. What do you do about pointers? Do you want to send those around? Maybe, maybe not. But in general, what's the hard part about sending a pointer? What happens if I do send a pointer and I have something over here? Let's just hypothesize. Let's say I had something that was a pointer and I just said it's 32 bits. 32 bits of memory plus some process ID. What happens if I send that over to the other side?
It's useless without the server then communicating back to the client to get whatever's there. And
right. So why would you send the pointer? What's the use of a pointer? You want to dereference it, right? What happens when how do you dereference this pointer and figure out what it's pointing to? You have to go back, right? So why not send the thing that you're pointing to in the first place over there, right? So so that, I mean, from that sense, you probably don't want to be sending pointers over. There are times when you do want to be sending pointers over, and it's okay. Can you give me an example of that?
If it doesn't actually need to access it, but it might need to do pointer arithmetic to, when it returns whatever it returns, we'll have to access.
Yeah, so maybe like in C, if all you're doing is pointer arithmetic, you can kind of fudge the pointer as an integer and send it over. And if there's no dereferencing, then it might be okay. Another example is, imagine that the thing you're pointing to is actually something not necessarily that's here, but that's in some. Let's suppose that there's some other big object repository. So in the virtual memory for object-oriented systems, they talk about these object-oriented systems. There's a lot of research that's actually been done on having these gigantic, replicated, available object repositories spread around. If you're sending pointers into these that reference objects, then, well, this thing is supposed to be distributed and available, etc. So if you send a pointer to one of those, then it might not be so bad to do that, because then you can just reference it here. In fact, the server might even have a local copy, or could cache a local copy. So you have to be very careful with pointers, but there are times when it doesn't make any sense whatsoever, and there are times when it actually makes a lot of sense.
So, Luis, do you determine locally then whether or not to make a remote procedure call just based on sort of the overhead of sending all of your argument data out versus whether it's faster just to do something locally?
Yeah, that's something. If for example, if you're doing a big computation and one of your objectives is performance, then you'll have to take that into consideration. If you want to send, the cost of sending that out shouldn't be greater than the cost of doing it yourself. And if the thing that you're sending out is this big hunkin' array, right, then that server better be doing a lot of work on that array, or else you might as well just do it locally. Now, one thing that can happen is you can get exceptions, and when you do this call, you might get back exceptions. One of them might be a timeout. One of them might be an anticipated failure. You might get a network type of exception. There's all sorts of different types of things that can hit you. And how that's handled depends on your system. And some of them, these stubs handle them, and there's always just like a fail message that comes back. Sometimes you might actually want to get a little bit deeper into the details of what actually happened so that you can try to fix it yourself within the program. Okay, now that we've talked a little bit about this about RPC, I want to close up talking about end-to-end design. This is a debate that actually started off a while ago and is still going on. And it's one of these key debates that's very good to understand, because it'll permeate any kind of system design that you do. How this first idea, this end-to-end design idea, first came up. So when they were when trying to decide what kind of protocol to use on the internet. Remember, back in those days, what did people do with the internet? Well, typically they would log on somewhere. That's what you used it for. You'd log on to your machine here, your server there, your server there. You might do a little bit of FTPing, but there was most of the users used it in some form or other for these sessions. So the idea of a session, if you imagine trying to build the idea of a session into the internet infrastructure itself, what would that mean? Well, a session is a lot like a virtual circuit, like the phone company does, right? It just opens up a dedicated line, connects the two together, and then you just go from there. And what's great about that is that once you have that line, you know that you have a certain amount of bandwidth. You know that the performance characteristics become a bit better defined. So if you don't have, for example, if you don't have enough bandwidth or if there isn't enough capacity, you'll get a busy signal, just like the phone. So imagine if you try to build that type of thing into the internet, where every time you made a connection, you ended up creating, in essence, a virtual circuit like the phone companies do when they connect two parties together. Why would you want to do that? Well, one of the arguments being proposed at that time was, well, everybody does it for this, and everyone's always going to want to do it for that, and it's expensive to implement, and software, you can come up with a bunch of other reasons why they might say that, but they basically wanted that at the lower layers of the internet. Some other folks on the other side, and you'll read one of their papers, had a different idea. They had this end-to-end argument, which is that these functions that you want, like sessions and flows or whatever else might be, most of them can actually be built on top, layered up on top at the ends where they're being used. So there's no reason why, if you had a very simple lowest layer that just did, say, packets, that you couldn't, at the server side and at the client side, create the notion of virtual circuits and then have some kind of implementation on top of these simple unreliable packets. The reason you'd want to do that is because you don't know what the network's going to be used for later on. What happens if, for some reason, people stop using it for sessions and start using it for something like HTTP, which they didn't know about back then? What would happen to the performance of the internet if every time you made an HTTP connection, that was supposed to be a virtual connection like on the phone?
If you managed to get a connection, performance would be great.
If you managed to get a connection. Yeah, but yes, but imagine when you get a page, when you download a page, some of these go off and they talk to DoubleClick, they talk to a bunch of different servers. So think of it another way. When you dial a phone number, how long does it take for you to actually get connected? Is it a millisecond, or is it more like a second? It's a little bit longer, right? Imagine if every one of those times you went off and you had to get a URL from somewhere else, it took that long just to set something, just so that you could download a little, a tiny little GIF from somewhere. It'd be horrible. So what the argument here for end-to-end design is try to keep the middle part, the substrate that you're building, as simple as possible, and only build up functionality at the ends where you actually need it. This will give you more flexibility, and it'll leave the intermediate pieces available for better performance, better optimizations. There's a paper you'll have to read about this. I'm just bringing it up in lecture because it's just a very fundamental design concept that's helped us greatly in terms of being able to scale out the internet. And this is one of those papers you guys should really enjoy, but also try to get a lot out of.
You said that this question about end-to-end design was sort of an ongoing debate. Although it looks like for the web, at least, that end-to-end design is clearly the way to go. So what is the ongoing? There's
the internet too. That's the other thing is, the argument is resurfaced with internet too, is what kind of functionality do you want to build into that? Do you want to build in streaming capabilities? Well, that'd be great, because then you could stream, voice and multimedia, but is that what we're going to be using it for in 20 years? I don't know. 20 years ago, people thought everyone was going to be using sessions. That was going to be the majority, and everyone was completely convinced. And I'm pretty convinced right now that we are going to be using multimedia in 20 years, but who knows? Yes.
The whole things like cookies and stuff like that are a huge commercial impetus to try and mimic state on the web, because if you're Amazon, you want a cookie so that you can immediately plug into someone's previous history, shove the books that you think they're most likely to buy at them, give them peer group recommend, all that's kind of mimicking state.
Yeah, the other argument is, let's suppose that everyone just universally agreed that we were going to be using streaming in 20 years. Even then, the problem is that if you build that streaming into the lower layers of the internet too, then there's going to be some kind of cost associated with people who want to use that for a purpose other than streaming. You can imagine there being some other, maybe there's some other services where all the streaming overhead causes a huge performance hit, and all of a sudden those services become less attractive, and that's all because because they didn't follow the end-to-end design. And it's a huge debate. I mean, there's all sorts of money to be made if everybody agrees to put cookies and streaming and everyone's favorite stuff directly, because that means less implementation overhead for a lot of, all these commercial reasons. But from a practical point of view or forward-looking point of view, it's a very different decision. Other questions? Okay. Well.